It's worth examining a little more closely why we use the regression line and no other to make our estimates. For the football-shaped scatter diagram, and those of you who like looking at numbers on axes will notice the standard units on both sides. I like working in standard units. For the football-shaped scatter diagram, the regression line picks off the centers of the vertical strips. And that's a good thing to do for estimation for reasons we've discussed many, many times. But maybe there are other good things to do? Why is that the only thing we could do? Surely we can use any line we think is a good idea, and I think this one might be a great idea. You don't like it? Well, it's okay. It's a free country. I get to draw any line I want. But I'm willing to examine why you don't like it. And in some general sense, it seems as though it is not as close to the scatter diagram as the green line. And if we can examine that a little more closely, that will help us quantify just how good the regression line is. And in fact, it turns out that it is good not only for the football-shaped scatter diagram, but in a sense, the best you can do for any shaped scatter diagram. And so let's examine how all of that can be made precise. So what I'm going to do is put both of the lines on the same diagram, and now the object still is to estimate values of y given values of x. And here is where you see the green line doing much better, because, for example, if you take a point like one of these, then they are not so far from the green line. To get from the point to a green line, you come down about this much. But to get from the point to the corresponding point on the red line, you have to go a long way down. It's right there. So these 2 points are much further from the red line than they are from the green. And I'm looking at vertical distances, of course, because our estimates are on the line. The actual points have their values of y in the vertical direction. And that is the sense in which this red line is further away from the scatter diagram in general than the green line is. I mean, it's true that some points, this one, for example, is closer to the red line than to the green one, as is this one. But by and large, if you look at all of these, right, they're very, very close to the green line. And even those that are far from the green line are much further from the red line. And so the idea is to quantify how good a line is in estimation by looking at the vertical distances of the actual points from the line and getting some sense of how big those distances are. Now, the distances may be positive or negative or zero. And nevertheless, for every point there is a distance. And so if we summarize what we've just seen, you pick the line you like best to use for estimation, and you put it through the scatter diagram. Then for every point in the scatter diagram, your line makes an error, and that is the vertical distance between the point and the line. And we just observed that some of these errors are positive, some are negative, and some are zero. And if you've got a list of positive and negative numbers, errors typically, and you want to know roughly how big those errors are, then what do? You've done it before. Exactly, we did it with deviations. You take the root mean square of the list. That gives you a rough sense of the size without regard to sign. And so what we're going to be computing is the rough size of the error quantified by the root mean square of the list of errors. And it turns out that there is a wonderful math fact that says that if you look at all the straight lines that you could possibly put through your scatter diagram, any scatter diagram at all, you look at all the straight lines you could put through it. You could put any straight line at all through it. Associated with every one of those lines is a root mean squared error. Some are very large, those lines are terrible. Some are small, those are the ones you want to use. It turns out that for every scatter diagram, one line beats all the others in terms of RMS error. It has the smallest RMS error among all straight lines. And which straight line is that? Yep, it's the regression line. And that is why the regression line is used rather than any other. It is the least squares line. It makes the smallest mean squared error among all straight lines. This happens to be true regardless of the shape of the scatter diagram. Now, of course, for the football shaped scatter diagram, that's particularly useful because you can use your line for estimations throughout the range of X. So it's the best among all straight lines. That's the good news. But every time we have some good news, it's worth noting what our constraints are. Exactly what have we concluded? The best among all straight lines is not necessarily the best among all curves. So let's not get carried away. So for example, here I made an artificial example. Suppose my scatter diagram is this set of dots which I made into a beautiful parabola. That's just an ordinary old scatter diagram, and I can put lines through it. Should I put lines through it? No, of course I shouldn't, but supposing I do anyway. Because let me tell you, people do it all the time. I can put any line I want through it, and associated with any line that I put through it, there's an RMS error. And it turns out that the best line, the regression line, is flat. Right there. That is the best among all straight lines. So nothing really. You don't want to use the line in the first place. It's the best of a bad lot. So the moral of this story is, no matter what the scatter diagram, you can calculate the regression line. That doesn't mean you should use it. We're back to where we were when we were discussing correlation, and we said if the scatter diagram is not linear, then don't use the correlation coefficient. Well, the regression line is based entirely on that. So if the scatter diagram is not linear, then don't fit straight lines. This obvious thing, and you're all sort of rolling your eyes and going, get on with it. I already know that. I'm very glad to hear it, because this simple thing is ignored in many, many analyses. So people don't draw the scatter diagram. They go to Excel, you know all about going to Excel and other computer packages. They go to Excel and they push a button and out pops the equation of a line. Before you do that, please draw the scatter diagram. If the scatter diagram happens to be linear, then the regression lines